Okay, so we're going to talk about the nervous system this week, and we're going to talk about specifically, we're going to talk about the nervous system. We're talking about neurons and how action potentials are fired. We're also going to talk a little bit about how we receive those action potentials or those messages from our neurons, and how we interpret them and then we respond to them. The nervous system is very, very complex, and it's something that we're going to go over for at least another week. So this week we're basically going to focus on action potentials, and that can be a really hard concept to understand. So I've incorporated lots of videos and different things to help you understand it. So first of all, we need to talk about what an action potential is. We need to talk about neurons, and that should be something that is very familiar to you because you've done a couple of things on tissues, and in each one you should have learned about neurons. And neurons are the cells of the nervous system. And they actually are what are responsible for us to be able to feel pain and smell and or to smell things and to see things. These are neurons are responsible for all of that. To feel touch. These are all the only reason we're able to feel and respond to these things is because of neurons. And neurons are just the cells of the nervous system, and masses of the neurons put together will form a nerve, and they transmit information, which that says right there. The cell body. So neurons made up of a cell body. It contains a nucleus and two extensions. You'll have dendrites, which are extending off the cell body, and then you'll have an axon. And this axon is a single long fiber which conducts impulses away from the cell's body and sends information. So what you'll see here is that these are actually going to be connected to each other, and down here at the bottom you'll actually find another cell body down here somewhere. And how we're actually able to transmit this information is this nerve will get the impulse, and it will send it down through the axon, and then through the dendrites, and that dendrite will actually stimulate another dendrite, and that will travel down the axon, and it'll do that until it reaches its destination. Okay, so we're going to talk a little bit about the two types, or the nervous system in general as a big whole. We'll talk more about that next week. So I'm just going to touch on it a little bit here. The central nervous system, or the brain, is composed of the brain and the spinal cord. Okay, so our brain and our spinal cord, when we talk about the central nervous system, it's just that. It's the brain and the spinal cord. The peripheral nervous system are the nerves of the body. Okay, so we actually have 31 spinal nerves and 12 pairs of cranial nerves. And here we have our spinal cord and our brain, and then we have nerves coming off of our spinal cord. Okay, so there are three functions of the nervous system. We have the sensory, which gathers info. We have the integrative, which the information is brought together, and then we have the motor, that responds to signals. and it's responsible for maintaining homeostasis. Okay, so here we have our sensory input, and that's, our body telling us I'm thirsty. Okay, so that travels down to our integrative, um, where it's actually put together in the brain, and it sends out another impulse, and this is our motor output that says I need to drink some water. And that's, picking up the glass of water to drink it, or going to the kitchen and pouring that glass of water. So motor functions, we can actually put that into two different categories, and these are all part of the peripheral nervous system, and that's the somatic nervous system, which is the skeletal or the voluntary nervous system, and this is like actually what we do, and we mean to do it. And then we have the autonomic nervous system, which is the smooth muscles, the glands, and this is involuntary. And this is actually how our body maintains a lot of its functions, breathing, a heart rate. These are all part of the autonomic nervous system, and these are things we don't think about, or we need to think about to do. Our somatic nervous system, now that's something we think about. Okay, that's actually telling our muscles to move, sending that impulse to the skeletal muscle to move. Now we're going to talk about neuroglia cells. They support cells for the neurons, and sometimes they call this the nerve glue, because they support and protect neurons as well as doing other things. So the first one of these cells are the micro glial cells, and they're scattered throughout, and they digest debris or bacteria. They offer an immune response for the nerve cells. Here we have the oligodendrocytes, which make up the myelin sheath that provides insulation around the axon, and that just kind of insulates the axon and helps with that action potential, or that nerve impulse. It helps it along its way down the axon. And then we have astrocytes, which connect blood vessels to the neurons, and we also have epidermal cells that form a membrane that covers brain-like parts. So you'll see those in the brain, and you'll also see those in the spinal cord. Schwann cells, which form an insulating myelin sheath around neurons. The myelin sheaths, these serve as insulation around the axon. Schwann cells supply the myelin for peripheral neurons. Oligodendrocytes myelinate the axon of the central nervous system. So you'll find the oligodendrocytes in the brain and the spinal cord, where you find the Schwann cells in the peripheral nervous system, and they pretty much do the same thing. They provide this sort of insulation for the cell. So this myelin sheath creates an insulation so that electrical impulses can actually travel along faster, and also provides a type of protection for the nerves, so that if you damage a nerve cell, they rarely divide, and a little bit of damage will repair But if you say severed a nerve or a neuron, that's not going to grow back, and that's not going to recreate itself. Um, so having a little bit of protection there, that these sheaths offer, that is helpful. So here we just have the supporting cells. And here's just some more pictures of them. Okay, so now let's talk a little bit more about neurons. Okay, so just a little bit about neurons. We've already talked about they have the cell body. They have their dendrites where they have the receptive region. And then we have our nucleus, which also has a nucleolus. Our axon hillock, our axon, which travels down here. We have our myelin sheath, which covers our axon, and then we have our nodes of Romvia, which are the spaces in between the myelin sheath. If you can kind of see that on there. And then we have our axonal terminals. So this is the this is where, and we're going to talk about in just a minute, where it's going to secrete that neurotransmitter the dendrites on the other neuron will pick up. So again, this is just talking about the neuron, and what a lot of people like to compare it to is your hand. So you'll have your axon, which is, we've already said, the very long part that extends down from the cell body. And I like to think of that as my arm. And then I like to think of the cell body as the palm of my hand, and the dendrites as my fingers. So again, we have that myelin sheath, which is insulation surrounding the axons, and myelinated neurons compared to unmyelinated neurons actually are able to transmit nerve impulses faster. And then we have our nodes of Romvia, which are the gaps in the insulation, and you can see them right here. Here we see our gaps. If we're looking at a cross section of the brain, or even the spinal cord, you're going to see white matter, and you're going to see gray matter. And white matter is going to be those neurons that have the myelinated axons, and the gray matter is actually the unmyelinated axons. And then here we have actually a picture of a neuron that you will need to label in the next assignment. So if you're looking here, a couple of things that we can identify right off the top is we see the cell body is right here. We have the nucleus, our dendrites. We have the nodes of Romvia, the Schwann cells. We have our axon terminal. We're going to have our astrocytes. And then we're also going to have some of those microglial cells. And again, just to recap, we go back, we have our astrocytes, and those are going to connect blood vessels to the neurons. And then we also have the microglial cells, which actually act in an immune response. They're actually what we call phagocytes, meaning that they'll digest debris, bacteria, foreign particles, and kind of protect the neurons. Okay, so here we're talking about neurons' longevity can live and function for a lifetime. So, like I was saying before, they do not divide or renew. The neurons that you're born with are the neurons that you're going to have for maybe 60, 70 years. They do not divide. And they have a high metabolic rate. So they require abundant oxygen and glucose. So just to kind of build on that, I don't know if you've ever heard of this, but if you've severed your spinal cord, or you have a spinal injury, that often paralyzes you. And the reason for that being is that these cells do not divide. So if you do damage them, that's something that you will live with for a lifetime. Depending upon where the damage is, depends upon the injury. For instance, if we have them in our lower back, if we were going to sustain an injury, it would be better to the lower part of the spinal cord, because this is supplying peripheral neurons to the lower part of the body. Whereas if you have them, you sustain an injury to the upper part of your spinal cord, you're going to damage those nerves. And that, remember, we're talking about a peripheral nervous system, which controls both the somatic and autonomic systems. So autonomic meaning that we might not be able to breathe if we sustain injuries up in here, and we would need help in doing so, and also our somatic, which means arms, legs, etc. Okay, and this is just displaying the pathway of the nerve impulse. I think we explained this just a little bit before. So say if we were hearing something, the telephone, we would receive that stimulus in our ear, and we would have sensory neurons that would carry that impulse to the CNS, or the central nervous system, our brain, and we call those neurons actually afferent neurons. So they receive the nerve impulse, and then they'll send a stimulus back to our hands, or to go pick up the phone. We call those afferent neurons, or efferent neurons, efferent neurons. So here we have again the neurons, and here we have the axon of a previous neuron, and here we have our terminal. And this is when one axon ends and is connected to a dendrite, and they're actually not completely connected. We call this a synapse, and we'll talk about the synapse here in just a minute. And you'll see the synapses here, and they'll start the electrical signal, and then we'll have the synapse, and it will send that what we're going to talk about, a neurotransmitter, onto this cell, which will start that electrical signal or the electrical impulse down this cell, and then we'll get down to the synapse, and it'll secrete what we'll talk about in just a minute, the neurotransmitter, and it'll start on this cell. Okay, so now we're going to talk about the cell membrane potential, the resting potential, the threshold potential, the action potential. We're going to talk about the nerve impulses, and we're going to get into some heavy stuff here. Okay, so on our neuron, we actually have, and I'm going to go ahead and explain this first. On our neuron, on the inside of the neuron, we have what potassium ions. These potassium ions are negatively charged, and on the outside we have sodium ions, and they are actually positively charged. And you guys are actually going to watch another Bozeman science guy video, and he refers to this as a salty banana. Okay, and all that means is you have sodium on the outside, which we relate to with salt. Bananas are high in potassium, so we have potassium on the inside. And if you guys can remember that, then you'll be good. So at resting potential, we have our negatively charged potassium ions on the inside and our negatively charged sodium ions on the outside. So at resting potential, like I said, we have our sodium on the outside and our potassium on the inside. We have a positive charge on the outside and a negative charge on the inside of the neuron. So what happens is the neuron will receive a neurotransmitter that tells it to open up its sodium channels. And what will happen is a few sodium will come into the inside of the neuron. And when it comes into the inside of the neuron, what will happen is it will make it positively charged. Okay, so what we have here at resting potential is we have somewhere around negative 70 voltage, okay, millivolts here. All right, and when we add some of these sodium ions in, what happens is we create a positive charge. Okay, so each time that we add some of those sodium in, we add a positive charge. And this actually is what starts an impulse, okay, and what actually causes what we call an action potential, or the signal to travel down the axon. So we have more sodium coming in, and once it reaches negative 55, we have reached what is called threshold. And once threshold is reached, then we can actually start the action potential. But if threshold is not met, meaning that not enough sodium ions have traveled into the axon, and it hasn't reached that voltage yet, then we're not going to start that impulse. So here we have our resting potential, and we have our negative potassium ions on the inside and our positive sodium potassium ions on the outside. And we're at resting potential, the membrane's actually resting. A stimulus initiates the depolarization, and this is just a term used to talk about the potassium ions traveling in. Depolarization and generation of the action potential occur. So sodium ions start to enter, and what that means is we start to get a positive charge on the inside, and these positive charges on the inside actually initiate more of these sodium channels to open on down the axon. Okay, so the neural membrane maintains resting potential. The threshold stimulus is received and the sodium channels open. Sodium ions diffuse inwards, depolarizing the membrane. The potassium channels also open. Potassium ions diffuse outward, repolarizing the membrane. The resulting action potential causes a local bioelectrical current that stimulates adjacent portions of the membrane. So then there's also a wave of the action potentials travel the length of the axon of the nerve pulse. Okay. So at rest, the inside of the neuron's membrane has a negative charge, as the figure shows. Sodium-potassium pump in the cell membrane pumps sodium ions out of the cell and potassium ions into the cell. However, more potassium ions leak out of the cell. As a result, the inside of the membrane builds up a net negative charge relative to the outside. Okay, so nerve impulse. So the speed of the nerve impulse is proportionate to the diameter of the axon. The greater the diameter, the faster the speed. Myelinated axons, as I said earlier, conduct faster than unmyelinated ones. Okay, and then like we were talking about before, we have the synapses, which are junctions between the two cells. And this is how they communicate with each other. It's kind of like a tag, now you're it type deal. Or if you've ever seen where, you're past the egg game where you take the egg to someone else, well, they're taking the nerve impulse to the next neuron, and so on and so on. And like I just said, the nerve pathway, it travels from one neuron to the other, from the dendrite to the cell body, along the axon, the synapse, dendrite again. To complete the signal, a neurotransmitter is released at the gap to signal the next neuron. So this is how they actually signal the next neuron. What we call a neurotransmitter is actually released at that synapse, and receptors on the dendrite receive the chemical message. So we have something called a receptor, and it's actually going to receive that chemical message. So here we have mitochondria and microtubules, our basic cell components. Here we have the presynaptic axon, presynaptic axon right here, or density, synaptic cleft, and then postsynaptic dendrites right here. So we have two types of neurotransmitters. One are called excitatory, which increase membrane permeability, increase the chances of threshold to be achieved. So what happens is they excrete this neurotransmitter, and it actually sends that nerve, it tells actually the sodium ion, or the sodium channels to open up, and then it tells it to get this process started. We have inhibitory, which decrease the membrane permeability. So they decrease the chances of threshold to be achieved. They decrease the chances of an action potential to be actually achieved. And these inhibitory will actually bind to the receptors on the ion channels, and it'll tell it not the sodium channels not to open, and actually create that nerve impulse. And just I was going to show you guys something, but now I've forgotten. Okay, so here it's just showing you again. We have our neurotransmitters it's releasing. Here are receptors or on the channels of the sodium pumps. They're receiving it. And this is actually displaying, well, excitatory or inhibitory, and whichever that might be. If it's excitatory, it's going to tell it to open up those channels and receive those sodium ions. If it's inhibitory, then it's like, no, don't come in. It's going to close it and actually tell it not to come in. And just what I was talking about before, with this, we were talking about action potentials to be achieved, and I said before we have to reach a -55 for that action potential to actually be achieved. And what will happen is at resting, we're at like -70 here, okay? And we have the sodium coming in, making a positive charge. The sodium coming in actually creates a positive charge inside, and it will boost it up to that -55. Now, if we don't get enough sodium pumps to open up, then we do not reach -55, and we do not pass go. So that's a no-go for the action potential. It has to reach -55, and then bam, an action potential occurs, or an electrical impulse is traveling down the axon. Okay, so what you should have picked up from the muscle system, and it's kind of, backwards, because we talk about a lot of things in anatomy and physiology that you need prior information on. So I tried to put as little as I could about the nervous system and the muscles unit, but there is a little bit in there, and one of those things that we talked about in neurotransmitters, acetylcholine, which stimulates muscle contractions, and we talked about neuromuscular junctions and the neuron releasing the acetylcholine onto that junction, and creating the muscle, causing the muscle to contract. Also talk about norepinephrine and dopamine. These give you a sense of feeling good, or if you have low levels of these, it often creates depression. We have neurotransmitters, serotonin, which cause sleepiness and mood. It has a lot to do with our moods. Endorphins produced during exercise give us excitement, pain, love. They resemble the opiates in their abilities to produce a feeling of well-being. The name endorphins comes from endo and orphan, intended to mean a morphine-like substance originating from within the body. And there's actually poisons made from frog skin that can cause paralysis by blocking acetylcholine receptors at the neuromuscular junction. We're actually going to talk about that a little bit next week. I thought it might be too much for this week, but next week we're going to talk about that. We're going to talk about that. Snails actually do the same thing in fish sometimes. Okay, so Poisoning can be fatal to humans, animals, and can occur by inhalation, swallowing, or absorption through the eyes. So we have neurotoxins that can act as an antagonist of acetylcholine receptors, and it primarily affects the motor nerves in the spinal cord, which control muscle contraction. An impulse is triggered at one end of the nerve, binding by the neurotransmitter, the receptors. Okay, so when we talk about Zoloft, it is a part of the class of drugs called selective serotonin reuptake inhibitors, or SSRIs for short. SSRIs act as a specific chemical within the brain known as serotonin. This is one of the several chemicals used to send messages from one nerve cell to another. So they mess with Zoloft actually messes with the neurotransmitters. And when it messes with the reuptake inhibitors, it inhibits the reuptake of the serotonin, so leaving more serotonin out there, hopefully making us feel better, because serotonin is also one of those feel-good neurotransmitters. Here we're talking about a neuronal pool. Groups of neurons that make up hundreds of synaptic connections work together to perform common functions. These pools help us remember sequential tasks like tying a shoe or riding a bike. Here we're just talking about sensory nerves that conduct impulses into the brain or spinal cord. We have motor nerves that carry impulses to muscles of glands, and we have mixed nerves that contain both sensory and motor nerves. Here we're just showing us we have our afferent, which is taking the nerve impulse to the central nervous system, where we have our our processing of the information. Then we send it back to the efferent neuron, or the efferent transmission, to the muscle glands, whatever is going to act on that stimulus that we just received. And just to go back just a little bit real quick to explain something. So we have our sensory input, which is controlled by the afferent. And then we have our motor output, which is our efferent. And then our integrative, which is the brain again. So here we have our reflex arc. It only includes a few neurons. A reflexive behavior is autonomic subconscious response. What happens is we, say, we've got that little hammer that the doctor puts on our knee. It hits our knee, automatically sends a message to our spine. Our spine automatically sends a message to our muscles to contract. Knee-jerk reflexes maintains uprightness, withdrawal reflex, avoidance of painful stimuli. So even without us really realizing it, sometimes we'll we'll have a withdrawal reflex before we even process. Sometimes maybe putting our hand on a stove or a hot stove, we'll pull it away before we feel the burn. And that concludes our nervous system. We also provided in the module several different animations to help you understand the action potentials in stimulus and neurotransmitters.